So in the last class, we discussed matrix chain multiplication problem. So we just recall the definition of matrix chain multiplication problem. So what is given as input here? We are given a chain of n matrices A1 to AN, where ith matrix AI has Pi minus 1 rows and Pi columns. Pi columns. So what is that we need to do? We need to find an optimal way of finding the product of this chain of n matrices, that is A1 to AN, using minimum number of scalar multiplications. So hence is it minimization problem or maximization problem? It is minimization problem. Is that correct? Okay. Now, if we consider matrices AI to AJ, in order to multiply this optimally, number of scalar multiplications required, if we call it as m of ij, then what is AI to AJ? AI to AJ can be written as AI to AK plus 1 to AJ. Is that correct? Then we consider that this part we need to multiply first or second. This we need to multiply. After multiplying both these two, we need to multiply again. So how many multiplications are required to multiply to get the first part? How many multiplications are required to get the first part? M of I comma k. How many multiplications are required to get the second part? M of k plus 1 comma j. So now after getting this AI to AK, what is order of AI to AK? 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 Number of rows here and the number of columns here, no? That becomes finally order of AI to AK matrix. So now you tell me what is order of this? What is order of this? How many rows are there in matrix AI? How many rows are there in matrix AI? How many rows are there in matrix AI? Pi minus 1 rows. How many columns? Pi columns. So this can be written as Pi minus 1, Pi minus 1. How many columns are there in matrix AK? How many columns are there in matrix AK? Pk. So what is the order of resultant matrix? Pi minus 1 Pk. Is that correct? Is that correct? Is there any doubt at this point? Similarly, what is order of AK plus 1 to AJ? What is order of AK plus 1 to AJ? What is order of AK plus 1 to AJ? Pk plus 1. What is order of AJ? Pj minus 1. Now what is order of AK plus 1 to AJ? Number of rows here times number of columns here. So what is order of this? Pk, Pj. Now we need to multiply these two matrices. How many multiplications are required? Pi minus 1, Pk, Pj. So therefore, what is the total number of multiplications? AI to AK, it is Mik. That's what we have got. AK plus 1 to AJ, this is Mk plus 1 comma j, plus Pi minus 1, Pk, Pj. But K can be anything, no? Okay, no. So that means immediately if I put parentheses like this, that means left side one matrix means k equal to I. If left side two matrices are there means k equal to I plus 1. Like this, k can vary from I to j minus 1. I to j minus 1. If I equal to j, how many matrices are, how many scalar multiplications are required? We are not doing anything, hence it is 0. So after doing this, what is the value that we need to calculate to find the product? M1 comma n. Is that correct? Is that correct? Is that correct? Okay. Now based on this, we can easily write a recursive algorithm. Based on this, we can easily get a recursive algorithm. What is this correct recursive algorithm? So what is that we need to actually calculate? What is that we need to actually calculate? What is that we need to calculate? Recursive matrix chain. Recursive matrix chain. P comma 1 comma n. This is our goal. This is our goal. So now general recursive algorithm we have written here. Okay, we have written here. So if I equal to j, number of multiplications is 0. Otherwise, number of multiplications, I take it some large value, say infinite. Now, for k equal to I to j minus 1, that is in the recurrence relation, no minimum of k I to j minus 1, that is for this, we are calculating what is q. What is q? Q is, yeah, this is mik, this is mik, this is mk plus 1 comma j plus pi minus 1 pk pj. So after that we get what is minimum here. So finally that becomes m of ij. We are returning m of ij. Okay. Now what is the time this algorithm takes? What is the time this algorithm takes? We can easily show that. Okay, we can easily show that it takes minimum 2 power n time. That means it is also exponential time. Brute force algorithm, that is also exponential. That is also exponential. Then we get doubt, why is it taking so much amount of time? So much amount of time. Now, if we know what are the solutions of immediate subproblems, for example, if we know what is answer to this, what is answer to this, what is the time we require to get the answer for this problem? What is the, if we know immediate answers for pik, pk plus 1 comma j, what is the time we require to get answer for pij? How much time is required to get answer for pij?
Order of 1, sir.
No, okay, let us go back to the recurrence again. Now you see, m of ij equal to minimum of k I less than equal to this one. So if I know this answer as well as this answer, what is the time we require to get m of ij? M of ij. So you wait. This is one value. This is one value plus this value plus this is another value. These three values we need to add now. That means what is the time it takes? What is the time it takes? Can you say that it is constant? Can we say that it is constant? Is that correct? Is that correct? Is that correct or not? Is that correct or not? So any doubt in this? So it takes constant time, but we don't know what is the value of k. No, this thing we need to repeat for each value of k, each value of k from I to j minus 1. This entire process we need to do for when k equal to I we need to do, that time it is constant. Similarly, when k equal to I plus 1 also we need to do, time also it is constant. Similarly, when k equal to I plus 2 also we need to do, that time also it is constant. And so on, when k equal to j minus 1 also we need to do, that time also it is constant. Like this, total how many times we are doing? Total how many times we are doing? Total how many times we are doing? How many times we are doing? We are performing this operation. How many times we are performing this operation? How many times we are performing the operation? Any answers? When k equal to I, we are performing. When k equal to I plus 1, we are performing. When k equal to I plus 2 also, we are performing. When k equal to j minus 1 also, we are performing. That means how many times we are performing? How many times we are performing this operation? Sigma k equal to I2 j minus 1 one time. What is this value? J minus 1 minus 1 plus j minus I minus 1 plus 1, which is same as j minus I. Are we performing j minus I times or not? Are we performing j minus I times or not? Is it clear why we are performing that operation j minus I times? We don't know for which value of k we get minimum. So for each value of k, we are finding the answer. Then after that, whichever k it value is minimum, that means here simply we are following brute force way. No, all possibilities we are calculating answers. Whichever possibility it is less, that answer we are returning. Whichever possibility it is less, that answer we are returning. Now, what is the time it takes? What is the time it takes? What is the amount of time it takes? What is the amount of time? Because here total j minus I options are there. J minus I times we need to do. Each time we require constant time. So j minus I into constant theta of j minus I. Can we write this? But j and I we don't know. No, we know what is n only. So what is the value of I? J minus I. What is the value of j minus I? We know that j minus I is less than or equal to n. Hence, this one, can we write it as big O of n? Can we write it as big O of n? So that means once we know subproblem solutions, to find a solution for the problem from which these subproblems have come, that we can do it in order of n time. Is that correct? Unlike Fibonacci method, where in constant time we can find a solution for a problem once its immediate subproblem answers are there. But here, how much time we require? Order of n time we require to find solution to a problem once its subproblem solutions are there. Is the difference clear? Is the difference clear? Is the difference clear? Okay. So now each problem, how much time it takes? If it's subproblem answers are there, why? Because unlike previous Fibonacci method, here we have a for loop. This for loop has to be run. No, once this is completed for each value of k, then only we know what is the value of m p, that is mij. This is nothing but mij value. No. So that's why this for loop it takes n time, order of n time, order of n time. This is again constant. This is constant. So overall it is order of n into constant. So it takes order of n time. Order of n time. Unlike Fibonacci sequence, nth Fibonacci number, that recursive algorithm, which was order of 1. Order of 1. Is the difference clear? Okay. Now you tell me, for example, if we want to calculate, say, product of, say, A, A4, A5, A6, A7, say something like this, we want to calculate the product. That means what is this value? What is this value? M, 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 4, 7. Is that correct? M, 4, 7. So what is our reconciliation? M of I comma j equals to minimum of k, I less than or equal to k less than or equal to j minus 1, M of I comma k plus M of k plus 1 comma j plus pi minus 1 pk pj. If I is less than or equal to j, zero or if I equals to j. Is that correct? Is that correct? Okay. Now, if we want to calculate m 4 comma 7, that means here what is the value of I? I is 4, j equal to 7. So what are the values we need to calculate? I is less than 7, 4 is less than 7 or equal to 7. This is correct. So which part we apply? This minimum of k, I less than j minus 1. No? So that means what are the values k takes here? What are the values k takes here? What are the values k takes here? K equal to 4. Next, k equal 5. Next, k equal 6. If k equal 4, what are the subproblems we get? If k equal 4, what are the subproblems we get? What are the subproblems we get? What are the subproblems we get? M I comma k, that is 4 comma 4. Next, M I plus 1 comma k, M 4 plus 1 comma 7. Is that okay? When k equal 5, what are the subproblems we get? M 5 comma 4 comma 5, 4 comma 5. K plus 1 means M 5 plus 1, that is plus comma 7. Is that okay? Similarly here, what are the subproblems we get? M 4 comma 6, M 7 comma 7. Is that correct? Is that correct? Again, how to calculate M 5 comma 7? 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 That means now I equal to 5, j equal to 7. How to calculate 5 comma 7?
K equal to 6, 5 and 6.
K equal to 5 and 6. Thank you, sir. Okay. K equal to 5, 6. If k equal to 5, then what is that we get? M 5 comma 5. Next, what is the other subproblem we get? M 6 comma 7. When k equals 6, what are two subproblems? M 4 comma 6, M 7 comma 7, M 7 comma 7. Okay, if we expand further, we can see further. Now, if you look at this, this and this, is there any repetition? M 4 comma 6, 4 comma 6. Is there any repetition? So there is a repetition, no? There is a repetition. So from this, it is clear that if we expand further, we can see more repetitions. From this, it is clear that there are overlapping subproblems. Overlapping subproblems are present. Overlapping subproblems are present. Now we'll see how many distinct subproblems are there. How many distinct subproblems? Number of distinct subproblems. How many distinct subproblems are possible? How many distinct subproblems are possible? What is that we are calculating? Our goal is to calculate M1 comma N. In this, how many distinct subproblems are possible? So say in general, we are calculating Mi comma J. What are the different values I can take? If I equal to 1, what are the values J can take? M1 comma 1, is it a valid subproblem? M1 comma 1, is it a valid subproblem? Is it a valid subproblem or not? Correct, no? 1 comma 1 is a valid subproblem. What about M1 comma 2? Mi comma J. I equal to 1, J equal to 2. Is it a valid subproblem? M1 comma 2 means what? In order to multiply A1, A2, how many are required? Next, when I equal to 1, J equal to 3, is it valid? Is it valid subproblem? Is that valid subproblem? Yes. J equal to 4, is it valid subproblem? Is it a valid subproblem? Similarly, what is last valid subproblem when I equal to 1? J equal to N minus 1, is it a valid subproblem? That means what? M1 comma N minus 1. That means A1 to AN minus 1. Is it valid subproblem? Yes. M1 comma N. That is A1 to AN. Is it a valid subproblem? That means it is original problem. That is also one problem we need to solve. No? So J can be N. When I equal to 2, what are the possible values J takes? What are different values J takes? When I equal to 2. When I equal to 2, J equal to 1. Is it valid or not valid? When I equal to 2, J equal to 1. That means what?
Not valid, sir.
M2 comma 1. Is it valid? No. Always I should be less than or equal to J. So this is not valid. This is not valid. J equal to 2. Valid. 3 valid. N also valid. Similarly, when I equal to 3, 3, 4 and so on N. And so on. When I equal to N minus 2, what are the values here? What are the valid subproblems? N minus 3, is it valid? N minus 3, is it valid? No. N minus 4, is it valid? N minus 4, is it valid? No, only N minus 2 or N minus 1, even N also. If it is N minus 1, what are valids? If it is N, what are valid? Is that okay? So how many distinct subproblems we have in the first case? How many distinct subproblems we have in the first case? Each combination is one subproblem. So N, how many distinct subproblems in the second case? N minus 1. How many distinct subproblems in the third case? How many distinct subproblems in the third case? N minus 2 and so on. How many distinct subproblems here? 3. How many distinct subproblems here? 2. How many distinct subproblems here? 1. Now you tell me total, what is the number of distinct subproblems we have got? Total number of distinct subproblems. What is total number of distinct subproblems?
Sigma n.
Total number of distinct subproblems. What is total number of distinct subproblems? N plus N minus 1 plus N minus 2 plus 3 plus 2 plus 1, no? Plus 1, which is nothing but N into N plus 1 by 2. That means we can say that it is theta of N square. Number of distinct subproblems is theta of N square. So that is number of distinct subproblems. We have got answer for this. It is N into N plus 1 by 2, which is same as theta of N square. It is. But what is the total number of subproblems we are solving? What is total number of subproblems we are solving in the previous algorithm, recursive algorithm? What is total number of subproblems we are solving? We have already calculated now. What is total number of subproblems we are solving? What is total number of subproblems? Is big omega of 2 power n. That's what we calculated. No, it is 2 power n or even more than 2 power n. No, even more than 2 power n. But number of distinct subproblems is theta of n square. Okay, no, number of distinct subproblems is theta n square. Total number of subproblems we are solving is big omega of 2 power n. Big omega of 2 power n. Is the screen visible?
Yes, sir.
Okay, okay. So what is total number of subproblems we are solving here? That is big omega of 2 power n, big omega of 2 power n. Number of distinct subproblems is theta of n square. Here itself we get doubt no. What is that we get? Okay, that means number of distinct problem is n into n plus 1 by 2, that is theta of n square. Total number of subproblems we are solving is the 2 power n or even more. That means the same subproblem we are solving again and again. We are repeatedly solving the same subproblem. Okay, that means what? That means what? If you draw recursion tree for some instance, we can see that there are overlapping subproblems. Now what is our goal? Now what is our goal? Now what is our goal? What is that we need to do now? What is that we need to do? See, number of distinct subproblems is n square, very less. Total time our algorithm is taking, or total amount of total number of subproblems we are solving is more. That means from that it is very much clear that there are overlapping subproblems. So what is the next step? What is next step? What is next step? What is next step? That means whatever recursive algorithm we have written, okay, no, that algorithm takes how? What is the amount of time that algorithm takes? Since there are 2 power n, more than 2 power n number of subproblems, it takes definitely 2 power n or more than that time, no? More than that time. That means exponential time. Now we'll get, okay, if at all, if I ensure that each distinct subproblem is solved exactly once. Okay, no? Each distinct subproblem is solved exactly once. What is the total time our algorithm takes? Similar to that Fibonacci, nth Fibonacci number, that problem, here also, if we ensure that each distinct subproblem is solved once. Exactly once. Okay. Each distinct subproblem is solved exactly once. Then what is the total time this algorithm is supposed to take? What is the total time algorithm is supposed to take? N into n plus 1 by 2, that is theta of n squared, into maximum time for a subproblem. Is that correct? Then I call this. Now we tell me what is maximum time for any subproblem. So that means this is one problem we need to solve. For this, whatever subproblems are required, all subproblem solutions are already available with us. Now tell me what is the time we require to find solution for this problem. So now let us look at the reconciliation. We need to calculate Mij. Mik answer is there. Mk plus 1j answer is there. Pi minus 1 Pk Pj. This answer is also there. So to add this, how much time we require? Theta of 1 theta of 1. Is that correct? Okay, here there is power cut and it's running on UPS. If it gets disconnected, no, then don't worry. Okay, so what is the time each distinct subproblem takes? For one value of k, it is theta of 1 time. Like that, for how many different values of k, we need to repeat this to find actual value of mij, minimum value for mij. How many times we need to repeat? How many times we need to repeat? K equal to I2, k equal to I2, j minus 1.
J minus 1.
J, that means total how many times? J minus I times. It is not more than n. It is not more than n. Is that okay? Not more than n. That means, can we say that we are going to repeat it order of n times? That means, what is that? We are going to repeat it order of n times, but each time it takes theta of 1 time. That means, in order to calculate m of ij, what is the total time it takes? Can we say that it is order of n? So that means, any subproblem, it doesn't take more than order of n time. Any subproblem, it doesn't take more than order of n time. Is that correct? Is that correct?
Yes, sir.
Okay. So now, what is the total time this algorithm is supposed to take? If at all we ensure that each distinct subproblem is solved exactly once. Exactly once. So it is
N cube now. N cube.
That is n square into big O of n, which we can write it as big O of n cube. That's what. Okay, now, so if we ensure that each distinct subproblem is solved exactly once, it is supposed to take n cube time only. That we can do it in top-down up method or bottom-up method. Okay, now top-down method or bottom-up method. Is it clear why n cube? Why n cube? So now it's say, for example, this is top-down method. It is top-down method. Here, what is the time this algorithm takes? What is the time this algorithm is supposed to take? What is the time this algorithm is supposed to take?
N cube time.
Initially, all subproblems are unsolved. Initially, all subproblems are unsolved. How many subproblems we have? How many distinct subproblems we have? N into n plus 1 by 2. So that means when for given I, what are values j takes? I plus 1 to n. No. For given I, j takes values from I to n. Sorry, I to n. Is that correct? I to n. That means when I equal to 2, what are values j takes? J is also 2 to n. Correct now? In general, we can write it as, but what are the values I takes? 1 to n. That's why this is for 1 to n. This is j I to n, m of ij equal to infinite. That means m of 1 comma 1 is infinite, m of 1 comma 2 is infinite, m of 1 comma n is also infinite. Similarly, m of 2 comma 2 is infinite, m of 2 comma 3 is infinite. All distinct subproblems, initially they are unsolved. They are unsolved. Okay. Infinite. Okay. Okay, one small instead of writing this, one more condition we can write here. Okay, before this will make it 7. Here we can write one condition. What is the condition we can write here? For I equal to 1 to n, what is that we can do? M of I comma I, can we write it as 0? For I equal to 1 to n, m of I comma I, can we say that it is 0? What is value of m of 1 comma 1? It is 0. M of 2 comma 2, it is also 0. And so on, m of n comma n, this is also 0. That's what we have written here. Is that okay? Is that okay?
Yes, sir.
Okay. So now Based on that, we can, this is simply called the same recursive algorithm, whatever we discussed there, same thing. So this algorithm takes order of n cubed time. Order of n cubed time, top-down algorithm, top-down method. Same thing we can ensure that in bottom-up method also. This is also, but this is bottom-up. What is the amount of time this algorithm takes? So this and all, okay, no, constant. So the 3/4 theta of n time, 5, it is repeated for each value of I, L from 2 to n one time. So it is small value only. Okay, this is repeated for each value of I from 1 to n minus L plus 1 one time, but this entire thing is repeated for each value of L from 2 to n. So we can simplify this. What about 9th? 9th, it is repeated for each value of k I to j minus 1 one time. This entire thing is repeated for each value of I from 1 to n minus L plus 1, but this entire thing is repeated for each value of L from 2 to n. This can we say, if we simplify, we can easily show that it is n cube. Okay, n cube. Other steps are anyhow simple steps only. So this operation is also performed the same number of times. Even this operation is also performed the same number of times. This is less than this many number of times. This is also less than this many number of times. So clearly we can, so without even knowing anything about this, can we say that this algorithm runs in n cubed or not? This algorithm runs in n cubed or not? This is one iterative algorithm. Okay, now this is some iterative non-recursive algorithm. We know how to analyze non-recursive algorithms without knowing anything. If this algorithm is given, can we say that it is n cubed? Can we say that it is n cubed?
Sir, what is the step 13 here?
Sir, any doubt?
13. So what is the step 13? 1, 3.
I'll come to that. Again, we will be revisiting this algorithm. That time I'll explain what is this.
Okay.
Okay. What is this S part? No, that this algorithm again we will be discussing. Okay. Now I am not going. I have not explained anything. I simply showed some algorithm exists like this, which is bottom up method. Still, it takes n cubed time. Top down method also it is n cubed time. Okay. Now we actually see how did we actually arrive at recurrence relation. Our goal was to calculate A1 to AN product using minimum number of scalar multiplications. Scalar multiplications. That was our goal. Okay. So what was our main observation? How did we arrive at recurrence relation first of all? How did we arrive at recurrence relation first of all? So here, what are valid subproblems? In general subproblem here, general subproblem we consider as AI to AJ. Is that correct? AI to AJ. AI to AJ. General subproblem we consider AI to, what is AI to AJ? Which is same as AI plus 1, AI plus 2, and so on, AJ minus 1, AJ. This is the chain of matrices from AI to AJ. That is AI to AJ. Is that okay? That is general subproblem. Now say someone has given optimal solution to it. An optimal solution to it. That means given an optimal solution to this. Someone has given, don't worry about who has given, say someone has given an optimal solution to this. That means in the optimal solution to this, they are going to multiply like this. AI to AK they are grouping, AI to AK they are grouping. Next, AK plus 1 to AJ they are calculating. Then these two they are going to multiply to get answer for AI to AJ. AI to AJ. Is that okay? Is that okay? Is the point clear? That means in the optimal solution, they are giving us some clue that after AK, there is a grouping. After up to AK, it is one group. AA to AK, it is one group. From AK plus one next matrix onward to last matrix, it is another group. So this has given us some clue. Because AK is part of our optimal solution, it is part of our optimal solution. We have got, this is someone has given, we have not calculated. And we know that AK is part of it. That means what? After AK, there is a parenthesis. After AK, there is a parenthesis. Up to AK, one group, after that, another group. Now, this AK, due to this, automatically we get subproblems or not here. Automatically we got some subproblems or not. What are subproblems? What are subproblems we have got?
AIK.
Now the question is, how to multiply AI to AK? This is the question. We don't know this. Next, this is AK plus 1 to AJ. How to multiply this? This is the question. This is the question. For example, say we are given 7 matrices, A1, A2, A3, that we are going to multiply with A4, A4, A4. Next say, let's say A5, A6 they are calculating first. That result they are multiplying with A7. A7. Okay. Now we have two groups. This is one part. This is some other part. Say our I equal to say 1 and J equals to say 7. I equal to 1, J equals 7. Now K we have considered it as 4. K we have considered it as 4. This is the optimal way of multiplying A1 to A7, say. This is optimal way of multiplying A1 to A7. A1 to A7. Now my question is, what is the optimal way for multiplying A1 to A4? That is, what is the optimal way to find the product A1, A2, A3, A4? What is the optimal way to find the product A5, A6, A7? Now these two questions it gives, that means original problem, that optimal solution, it has divided the problem into two sub-problems. In this case, two sub-problems. One is A1 to A4, what is optimal solution? We can ask. This is one sub-problem. Similarly, A5 to A7, what is solution? Now, what is the answer? What is the optimal way of multiplying A1 to A4? How to multiply A1 to A4? A1 to A4. What is optimal solution to subproblem? Optimal solution to it. Optimal solution to this. Or in general, what is optimal solution to? What is an optimal solution to? Optimal solution to AI to AK. Here, what is an optimal solution to? Optimal solution to AK plus 1 to AJ. What can you say about optimal solution to A, in this case A1 to A4? Now my argument is, whatever be the procedure they followed in order to compute A1 to A7 up to A4, that itself is the optimal way to find the product A1 to A4. This itself is the optimal way. That means this gives minimum number of multiplications. Similarly, A5 to A7, what is the method they followed? A5, A6 they calculated first. That result they multiplied with A7. This is the optimal, is optimal. Here we can say is optimal. Why it should be correct? Why it should be correct? Why it should be correct? say here it is taking, say, suppose 200 multiplications. I say that it is optimal. Why it should be correct? If at all that is not correct, if at all this is not correct, that means what? If this is not correct, that means what? There must be some other way to find the product A1 to A4, no? There must be some other way to find the product A1 to A4, which requires less than 200 multiplications. Which requires less than 200 multiplications. Let us, okay, no, for that, let us denote it like this. This is some way of multiplication where it requires, say, less than 200 multiplications. Less than 200 multiplications. This is the way which requires less than 200 multiplications. Okay, let us call it as, say, 180 multiplications. 180 multiplications. Okay. Now, what is the contradiction that we get in this case? What is the contradiction that we get in this case? Now, instead of multiplying A1 to A4 this way, if I use this way, so A1 to A4, we multiply it using this. Like this, we multiply A1 to A4. After that, A5, A6, A7, as it is, whatever they have given, we'll multiply like this. Now, this way, what is the total number of multiplications it requires? Up to this, we know that it is 180. Here, earlier also it was, say, 300. Now also it is 300. Plus, after this, how many multiplications we require? How many multiplications we require to find the product of these two? What is the order of this? P0, P4. What is the order of this? P4, P7 plus P0, P4, P7. This is the total number of multiplications. Is that correct? This is the total number of multiplications. That is total number of multiplications. Is that correct? Now, what is total number of multiplications? It is less than, earlier it was 200, no? Less than 200 plus 300 plus P0, P4, P7. Here, what is the number of multiplications in this case? This is 200, this is 300 plus this plus, again same, no, P0, P4, P7. So 180 plus 300 plus P0, P4, P7 is less than 200 plus 300 plus P0, P4, P7. Is that correct? That means we have got a contradiction to our assumption that this is optimal way of finding the product A1 to A7. We have got contradiction to our assumption that A1 to A7, that is optimal way. That means what? Why this contradiction has come? Due to our assumption that whatever given A1 to A4 is not optimal, we have considered. Not optimal, we have considered. Hence, our assumption is wrong. Whatever is procedure is followed to find the product from A1 to A4 in the original problem, the same thing is the optimal way of finding the product A1 to A4. That means it's a subproblem solution is contained within solution to original problem. Is that correct? Subproblem solution is contained within solution to the original problem. Similarly, the other side also we can show. This is actually called cut and paste method. Cut and paste. So using this cut and paste method, we can easily show that A1 to for this itself is the optimal way to multiply A1 to A4. This itself is the optimal way to multiply A5 to A7. Is that okay? Is that okay? So in general, now you tell me what is the optimal way to multiply AI to AK? What is the optimal way to multiply the AI to AK? Here, whatever parenthesization is followed, whatever method is, whatever order is followed, same order we follow and multiply. That itself is optimal. That means optimal solution to this is contained here. Optimal solution is contained is here itself. Similarly, this for this also optimal solution, whatever method they followed in order to multiply AI to AJ, same thing is the optimal way. So that means what is that we have shown here? Here, optimal solution to a problem contains within it optimal solutions to its subproblems or not? Optimal solution to a problem contains within it optimal solutions to its subproblems or not? Is it clear or not clear? Is there any doubt?
No, sir.
So then we say that the problem has got optimal substructure property or principle of optimality holds. So when do we say that a problem has optimal substructure? When do we say that a problem has optimal substructure? When do you say that a problem has optimal substructure? Optimal solution to a problem contains within it optimal solutions to its immediate subproblems. It's a subproblem, simply we can say it's a subproblems. Then we say that the problem has got optimal substructure. What is the advantage we get if it has optimal substructure? Optimal solution to a problem contains within it optimal solution to its subproblems. Then what? So what is the advantage that we get? By exploiting this optimal substructure, now the other side, one subproblem answer is known. What is AI to AK? What is optimal solution? MIK. What is optimal solution to this? MK plus 1 comma J. This is minimum number of multiplications to do this. This is minimum number of multiplications. After that, these two matrices we need to multiply. For that, anyhow, it is how many multiplications are required? Pi minus 1, Pk, Pj. So if we combine these three, this is going to give us what is the optimal number of multiplications for AI to AJ or not? AI to AJ. That means by exploiting this optimal substructure property, we can recursively define solution to a problem in terms of solutions to its subproblems. Is this clear now? You tell me whether matrix chain multiplication problem has optimal substructure or not. Matrix chain multiplication problem, whether it has optimal substructure or not.
Yes, sir.
Yes. So since it has optimal substructure, by exploiting this, what is that we can write? Mi comma J, we can write it as Mi comma K plus Mk plus 1 comma J plus Pi minus 1 Pk Pj. Is that okay? AI to AJ is divided like this. So we have got based on this. Is that okay? But what is known here? K gives minimum number of multiplications. But really, do we know what is the value of K? That is when somebody gives optimal solution. But actually, we only need to calculate now what is the value of K. So what are the values K can take? AI one side, AI plus 1 to AJ another side, or AI to AI plus 1 side, or AI plus 2 to AJ other side. Now, can you please tell me in general if it goes like this? AI to AJ minus 1 side, AJ at the other side. So that means what are the different values K takes? What are the different
I to J minus 1.
I or I plus 1, I plus 2, and so on up to J minus 1. So that we need to explicitly calculate. It is when somebody tells us that K is optimal, then directly we can write. But we don't know. No. Here, okay, when we are solving, we don't know. That's why each part, what are the choices we have for K? What are different choices for K? I plus 1 and so on up to J minus 1. For each value of K, we find solutions. then whichever, for each value of k, we find this value. For whichever value of k, this value is minimum, that we call it as our optimal choice. That we call it as our optimal choice. Is that correct? That we call it as our optimal choice. So what is optimal choice here? Minimum of k, I less than or equal k less than or equal to j minus 1. This is our optimal choice. That is the way we can minimum. Okay, so now by exploiting this optimal substructure, we have got a recursive relationship. Now, once this is known, you simply calculate what is m comma n, 1 comma n. That is solution to our problem. That is solution to our problem. Is that okay? Okay. Now, okay, one more example. All of you remember what is shortest path problem, no? Whether this problem has optimal substructure or not? Whether this problem has optimal substructure or not? This problem has optimal substructure or not? Say, okay, in order to show that, let us take an instance, say NITW, NITW to say Srinagar. Spelling is correct, Srinagar. Okay, NITW to Srinagar. Okay, this is an instance of the problem. This is an instance, NITW to Srinagar. We need to find what is shortest path. Let us assume that the shortest path value is, these are not exact values, I am giving here. Not exact values. Say this is 4,230 kilometers. NIT Warangal to Srinagar. Let us assume that it is 4,230 kilometers. Okay, na? And this is answer. And we also know that someone has told us that, say, it contains this path goes via say Delhi. This path goes via Delhi. Okay. Now NITW to this entire thing goes via Delhi. This much is given. Now, what are the two sub-problems we have got in this case? Now we can ask question. Earlier question was, what is shortest path from NITW to Srinagar? Now we can ask, what is shortest path from NITW to Delhi? Similarly, Delhi to Srinagar, what is shortest path? These two questions we can ask. What are these two questions? These are the sub-problems we got based on optimal solution to the given problem. Now you tell me, what is distance from NITW to Delhi? But these are not exact values. Again, I'm repeating. Okay, let us assume that this is, say, 2,800. Okay, so some route, this is 2,800 kilometers. So this is Delhi to Srinagar. This is, say, 1430. Total it is 300, 2,800, 4,230. No, correct only. No, okay. Now the question is, what is shortest distance from NITW to Delhi? What is shortest distance from Delhi to Srinagar? Can you tell me what is shortest distance from NITW to Delhi? Is it 200 or 2,800 or not? Here, is it 1430 or not? So this is our question. Is it 2800 or not? Is it 2800 or not? Think it's not optimal substructure, it's not clear to you. Okay, now I repeat. Okay, if at all 2800, it's not correct. It's not correct. That means what? That means what? There is some route from NITW to Delhi, which takes say 2700 kilometers. 2700 kilometers. That is say less than 2800. Let us suppose 2700 kilometers. So then what is that I do is from NITW to Delhi, instead of taking this route, I'll take this route, NITW to Delhi. After that, Delhi to Srinagar, same route I take. Then what is the total distance from NITW to Srinagar in this case? What is distance from NITW to Srinagar in this case? 4130. 4130. Is that correct? Is that correct? Is that correct or not? See, someone has already told us that NITW to Srinagar shortest distance value is 4230 kilometers. And they have also told us that that path goes via Delhi. Okay, now we can ask two questions. That is, NIT Warangal to Delhi, what is the distance? Delhi to Srinagar, what is the distance? Okay, now NITW to Delhi, the distance is 2800 kilometers. Whether it is correct or not. So someone said it is not correct. Then what I do is NITW to Delhi, that means there is some other route whose length is less than 2800 kilometers. So I take that path, let us say that path length is 2700. NITW to Delhi, I go via that path. Again from Delhi to Srinagar, same old path only we take. Then what is the total distance from NITW to Srinagar via this new path? 4130, which is less than 4230 kilometers, which we assumed as shortest, no? Which we assumed as shortest. But 4130, is it possible or not? 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 If you have any doubt, please ask me. Is that correct or not? 4130?
Yes, it is correct, sir. If there is a path from Warangal to Delhi, shortest path is 2700, then of course it is correct.
Then what becomes wrong? Our assumption that NITW to Srinagar, it is 4230 is shortest, that is optimal solution. It has gone wrong, no?
Yes, it is wrong, sir.
So it is contradicting with our assumption that this is optimal solution, no? If at all this path was there, then they would have said only 4130 is the shortest distance value from NITW to Srinagar. So
Yes.
this can go wrong. Our assumption that 4230 optimal solution is wrong. It never goes wrong, no? It never goes wrong. Hence, why did we get another path which is smaller than this? Due to our assumption that NITW to Delhi, there exists some other path whose length is less than 2800. But actually, is it possible? No. If at all it was possible, they would have said the shortest distance itself is not 4230. Hence what? NITW to Delhi shortest distance value is same path from NITW to Srinagar, You stop at Delhi. Up to that, whatever distance you covered, that itself is the shortest distance value from NITW to Delhi. Is that okay? Similarly, Delhi to Srinagar, that itself is the shortest distance. Similarly, so this is cut and paste method. Again, we are using cut and paste method. Cut and paste method. Is that okay? So that means what is that we have shown here? Optimal solution to a problem contains within it optimal solutions to its subproblems or not. Here we started with one problem. It has given two subproblems, and each of these two subproblems, no solution is contained within optimal solution to the original problem. Is that correct? That means what? That means what? What does it mean? What does it mean?
That means it's an optimal substructure.
Thank you, sir. Thank you very much. So that means shortest path problem has optimal substructure. Optimal substructure. Okay, optimal substructure. Okay, let us take another example. Say longest path problem. Instead of shortest path, longest path problem. This is A, B, C, D. Please tell me whether what is longest path from A to B here in this graph? What is longest path from A to B? Path means there is no repetition of vertices. What is longest path from A to B?
ACDB.
Thank you, sir. A to C, we can go C to D, D to B. Now our question is whether it has optimal substructure or not. We are going to check optimal substructure. Optimal substructure or not. So, for example, it is an instance of the problem where we are finding longest distance value from longest path value from A to B. What is length of path? Number of edges in it. Length of path is number of edges in it. In this case, this path length is 3. Okay,
Yes.
3. Now, my question. Okay. So we know that this longest path contains, say, some vertex called D. Now, tell me what is longest path from A to D. Similarly, this gives me two new subproblems. This gives us two new subproblems. We know that an element is part of this. Now, what is longest path from D to B? These two questions we can ask now. Longest path from A to D. What is longest path from A to D? What is longest path from A to D?
Length is 2, ACD.
What is it really correct? Now, instead of that, if I go via this, A to B,
A to B and then again D. It is also 2, length 2.
okay, let us put CD here. A, B, C, D, A to C. Oh, A, C, D, B, na? A. Okay, A is first, A to B, I can go. B to C, B to C, C to D. See, this is shortest path. longest path from say A to D, A, B, C, D. Now what is the question I can ask? What is longest path from A to C? A to C. What is longest path from C to D? A to C, C to D. What is longest path from A to C? I think A, B, C, it appears to be correct. Is that correct? What is longest path from C to D? What is longest path from C to D? Is it only one as given here? Is it one or not? Is it one or not? No, instead of that, I
So
can
for
go
A to
from
C,
C
for
to
A
D,
to
we can
C,
go B to A to D. Is that okay? So now, optimal solution to a problem, does it contain optimal solutions to its subproblems? Does it contain optimal solutions to its subproblems? Unlike shortest path problem, optimal solution to a problem, does it contain optimal solution to its subproblems? Here it is working correct, but this subproblem solution is not C to D, no, directly. This is longest path, no. Hence it doesn't contain. Hence, whether optimal substructure properties holds here, no. Longest path problem doesn't have optimal substructure. Shortest path problem has optimal substructure. Matrix chain multiplication problem has optimal substructure. In general, now, how to show that a problem has optimal substructure? How to show that a problem has an optimal substructure? So for that, we need to first to define general subproblem of that problem. General subproblem. How to define this general subproblem? It contains some parameters. So this is general subproblem definition. It should give original problem also. Original problem definition. After that, assume that something is an optimal solution to general subproblem. Something is an optimal solution to it. Now, after this, what next? This optimal solution, it contains an element. So based on this, the problem is original problem is divided into subproblems. Next, ensure that this subproblems solution is contained within optimal solution to the original problem. Subproblem solution is contained the optimal solution to general problem. That's what we have done now. Now please tell me what is this general subproblem definition in case of matrix chain multiplication problem? What is general subproblem definition? What is general subproblem definition?
Aij.
AI to AJ, how to multiply efficiently. Is that correct? AI to AJ, how to multiply efficiently. That is general subproblem definition. Now, whether this definition gives original problem definition also. If I take I equal to 1 and j equal to n, whether we get original problem definition from that?
Yes.
Yes, that is over. Next, assume that something is an optimal solution to the general subproblem. What is that we have assumed? AI to AK. It is something like this. There are some again parentheses I have not done. AK plus 1 to AJ. It is an optimal solution to AI to AJ. Then how many subproblems we have got? This is one subproblem we have got. This is another subproblem we have got. Now what is that we need to solve? AI to AK solution is this only. Okay, no, that means whatever procedure we followed here inside in order to calculate AI to AJ, same procedure we follow for AI to AK. Similarly, AK plus 1 to AJ. If that is shown, then we can say that optimal substructure property has been shown. Is that clear? But what is most important step here? How to define general subproblem? That is difficult. For that, we need to know the structure of, we need to characterize the structure of solution, then general subproblem, all those things. Okay. Now, what does this optimal substructure mean? All of you, please read this. This is the one that which I have been repeating now. So this definition, that means optimal solution to the problem contains within it optimal solution to subproblems. What does it mean? Indirectly, subproblem solution is there, this subproblem solution is there. Using this, I can find the solution to bigger problem. No, that is this second statement. Okay. Optimal solution of the given problem can be obtained using optimal solutions of this. This optimal solution, this is subproblem optimal solution. If you get optimal solution to original problem, this is subproblems, this is original problem. Then we say that it has optimal substructure. But this optimal substructure varies across problem domains. It mainly two things, important things we need to understand. How many subproblems are used in an optimal solution? In case of matrix chain multiplication, how many subproblems we used? How many subproblems we used in optimal solution? M of ij equals to M of ik plus M of k plus 1 comma j plus pi minus 1 pk pj. No. How many subproblem definitions we use? This is one solution. This is required. This is required. Two are required. No. But how many choices we have in determining which subproblems to use? How many choices we have in determining which subproblems to use? Because here k takes any value from I to j minus 1. That means how many j minus I choices we have now? Is that different? Is the definition of these two things clear? Is that clear, or any doubt in this? So based on that, by exploiting that, we have got this reconciliation for matrix chain multiplication. No. Now, next, by seeing this reconciliation itself, by looking at this reconciliation, easily we can write a recursive algorithm or not. And whatever algorithm, recursive algorithm that we discussed, we understood that it takes at least 2 power n time, at least 2 power n time. Then what is that we have ensured? Solve each distinct subproblem. Each distinct subproblem once. Why? Because here we got to know that there are overlapping. Solve each distinct subproblem once. This we can do it in either bottom-up method or top-down method. If we do it in bottom-up method, this is called dynamic programming. If we do it in using top-down method, it is called memoization. Memorization or is not there. That's all. So whether we use dynamic programming or memoization, what is our main intention behind this? We are going to ensure that each distinct subproblem is solved exactly once. We can do it in bottom-up fashion or top-down fashion. That's all. Okay. Next question is, okay, so in order to apply dynamic programming, what are the two important things the problem should have? In order to apply this, what are the two important characteristics the problem should have? It should have optimal substructure. What for this? If optimal substructure is there, based on that, by exploiting that, we get a simple, nice recursive formula for solution to a problem in terms of its subproblem solutions. After that, if there are overlapping, by ensuring that each distinct subproblem is solved exactly once, running time can be reduced further. Okay. So these two are the important things a problem should have to apply dynamic programming: optimal substructure and overlapping subproblems. If there are no overlapping subproblems, is it worth applying dynamic programming? Normal divide and conquer also okay, no? Normal divide and conquer method also okay. There is no. So now you please, all of you, read this. What does overlapping subproblem mean? I think this we discussed in last class also. No. So here next, in order to solve a problem by applying dynamic programming, we have actually 4 important steps. First one is characterize the structure of an optimal solution. What is that we have done in case of matrix chain? What does characterizing mean? Okay, AI to AJ solution, it can be obtained it like this. AI to AK you calculate, then AK to plus 1 to AJ you calculate, then automatically based on that. Next, once this is known, usually we will get a recursive formulation, no, M of ij. What is M of ij? That we have got. After calculating M of ij, what is the next thing that we need to do? We need to calculate solution to given problem, which is nothing but M1 comma N. M1 comma. What does M1 comma N give? It gives some integer as answer. But what is the order in which we need to multiply so that the number of multiplications is minimum? A1, A2, A3, A4, A5 is given. What is the best order we need to follow to get that order? For that, some additional work we need to do. That yes, whatever you ask to know, sir, that in matrix, that algorithm, that is for this step. See, we know that number of multiplications required is say some 3000. So what is the order in which we need to multiply so that we will get minimum number of multiplications? That we need to actually find, no? For that, we use this. That is that step. Construct optimal solution from computed information. Here we calculated 3000. Based on that, this order we should be able to print. Is that okay? Okay, I stop here. Okay. Again, last, we'll continue at 6:30.